Hi, my name is Dick Larson. I'm a faculty member at MIT, Massachusetts Institute of Technology in Cambridge, Massachusetts. Welcome. Today we have a very interesting problem for you. It's called Towers of Hanoi. It's a famous problem that has applications in computer science, in mathematics, and as we will see, in everyday life. Now, this is not a new problem. Towers of Hanoi was proposed in 1883 by Edward Lucas. You'll see on the table in front of me here, I have three physical representations of the Towers of Hanoi, what I call big, medium, and little. And we're going to talk about the rules of this game and what we're trying to do. And each of you should have a Towers of Hanoi in front of you. Now, these three were made professionally, and they cost some money, not too much, but some money to purchase. But you can make a Towers of Hanoi with just a minimal investment. It could be coins, 4 or 5 coins on top of each other, small ones and big ones. Or you could even make a Tower of Hanoi like this at home. And this about 3 days ago, I made this Towers of Hanoi in my home in Lexington, Massachusetts. And you might see a photograph or two of the production process, what's going on here. And basically, these discs in the towers are nothing more than washers that I got from a local hardware store. They just cost pennies a piece. And the wooden dowels here that I cut here cost less than $1. And this was a piece of wood that was left over. So you can make your own Towers of Hanoi like this if you want. Okay, so what is the problem? What are we trying to solve today? Well, let's look at this. What we're trying to do is move a set of disks like this. We're going to call each of these things a disk. Some have a smaller radius and some have a larger radius. Our chore is to move this pile of disks from here. We'll call this Tower 1. The medium one we'll call Tower 2. And this one on your far right we'll call Tower 3. We want to move these disks over to Tower 3. But we have 2 rules. We have 2 rules we must obey. We cannot move 2 at a time. We can only move 1 at a time, okay? Second rule is that anytime we have a pile of disks, we must have them in ascending order, the smallest one on top, the biggest one on the bottom. So this is not allowed, okay? But this is allowed. So those are the 2 rules we have to obey. And let's see how we're going to do this. Let's go over to the small one. Here we are with the small one, and we have a lot of disks. So let's not start with the largest problem. Let's start with the smallest problem. If we had to move this pile of disks, 1 disk, from Tower 1 to Tower 3, all I do is pick it up and put it over there. It took 1 move to do that. So that was easy, okay? Let's try it with 2 disks. Here we have 2 disks. How do I move this pile of 2 disks from Tower 1 to Tower 3? That's easy. I put this smaller one in a parking space, Tower 2. I put the larger one in its final destination. And then I take the smaller one off the parking space, put it over here, and solve it. That solves for the n equals 2 problem. So now I have a challenge for you. We have solved the n equals 1 and n equals 2 problem. Let's go to n equals 3. So in the tower in front of you, whether it's coins or washers or homemade tower, put 3 disks on Tower 1, obey the rules, move them over to Tower 3, discuss the strategy with your neighbors, okay, and record the number of moves it takes you to solve the problem. Okay, so solve the n equals 3 problem with the Towers of Hanoi, and do this in your class for 3 or 4 or 5 minutes, and we'll see you soon. Welcome back. Were you successful? Were you able to solve the n equals 3 disk problem? And did you talk to your neighbor? And did you keep count of the number of moves it took you to solve n equals 3? Well, and let's remember what the rules are. The rules are you can only move 1 disk at a time, and any pile of disks on Tower 1, 2, or 3 must be in ascending order with the smallest one on top and the biggest one on the bottom. So I hope you remember to obey those rules when you worked with your neighbor and yourself and you solved the n equals 3 problem. Now let me try to do it over here. So suppose I take the smallest one and I put it there, and I take the medium one, I park it over there, and I have to move the smallest one again. That's the only move I have. I put it over there. I'm not making much progress here. I'm not making much progress here. If I put that over there and this over there, this doesn't seem to be working. And look, what I've done is I've made the pile on the intermediate tower. Now, did I tell you when I first learned of this problem, the Towers of Hanoi, several months ago, it actually took me several hours to figure out the solution, and then the beauty of the recursion that we're about to talk about. So let's go back here and see if we can do a better job at this. So I take the smallest one and park it over there on 3. I take the medium one and park it on 2. And then I take the smallest one and put it on top of medium. And then I move just once the largest one from 1 to 3, its final destination. I take the smallest one, put it over there as a parking space, like this and like this. And lo and behold, I've done it. And it took me 7 moves. The first time I did it, it might have taken me 11 or 12 or 13 moves. So I want to know in your class, raise your hand if it took you 8 or more moves. Do I see some hands up? I think I see a few. And how many of you solved it in 7 moves? Oh, I see some more hands up over there. Good. And how many did it in less than 7 moves? No, I don't think that's true. It's impossible. So 7 is about the best we can do. 7 is about the best we can do. So let's look at this. Let's look at the size of the solution as n, the number of disks, grows. Remember when we had 1 disk, it just took 1 move, from 1 to 3. When we had 2 disks, it took 3 moves. Now we see the best we can do with 3 is 7 moves. Do you see some kind of pattern here in the number of moves we have to make to solve the problem as a function of the number of disks we have? Think about this. What kind of pattern seems to be emergent here? Why don't you write some of these numbers down on a piece of paper, talk to your neighbor, talk to your teacher, see if you can speculate what this pattern might be as we go forward to 5 disks, 10 disks, even 48 disks. Okay? Think about it, talk about it. We'll be back soon. Welcome back. I bet you had some fun with that. If you look at the pattern, 1 to 3 to 7, it's almost like 2 to 4 to 8. 2 to 4 to 8 is the power, it's 2 raised to a power, 2 to the 1, 2 squared, 2 cubed. So if you speculated that this problem doubles in size virtually with every disk, you'd be right. And so with n equals 4, 2 to the 4th would be 16, and then it goes to 32, 64, 128, 256, 512, 1024. That's huge. Now, it's a little bit complicated because our numbers don't exactly equal those. They equal those minus 1. So instead of 8, we have 7. Instead of 16, we're speculating 15. Instead of 128, we're speculating 127. But 127 moves? That sounds impossible, doesn't it? And that's very, very complicated. 127 moves here. So that's pretty scary. So we need to come up with some systematic way of thinking about this problem where the size of the problem doesn't get in the way of our thinking. So let's think about this. Let's go back to the sequence of moves we had with the n equals 3 problem. Let's look at what we did here. Small to right, medium to center, small to center, large to right, small to left, medium to right, small to right, done. Did you see any pattern there? How often is small moved? How often is the largest one moved? Remember, the largest one only was moved once from its initial destination to its final destination. What we want you to do is discuss this pattern with your neighbor, with your neighbors, with your teacher, and see if you come up with a pattern there that can guide us into having to solve larger problems with the Towers of Hanoi for larger values of n equals 4, 5, 17, whatever. Think about this, talk about the patterns with the neighbors, and we'll be back very soon. Welcome back. Did you see a pattern? I can tell you're really very much involved now with the Tower of Hanoi's problem. With your neighbors, with your teacher, you're really into it, and I think that's really good. Now, do you see a pattern that might help you for larger values of n? For larger values of n. Because we're going to see the beauty of recursion here. And this segment and the next 1 or 2 segments, we're going to go about and talk about recursion. And so let's go back and revisit for one more time the n equals 3 problem. So let's look at how we did this. We moved small to 3. We moved medium to 2. And we moved small over on top of medium. What have we solved here? We have solved the n equals 2 problem in 3 moves. Okay? Then we take the biggest one and move it once to its final destination. That's a 4th move. Okay? Now, we take the smallest one, we put it on its parking space over here. We take the medium, put it over here. Take the smallest one over here. 3 more moves. 3 plus 1 plus 3 is 7. So now you see what we've done in solving the n equals 3 problem. We solved the n equals 2 problem first. Then we moved the large disk to its final destination, moved it once. Then we solved the n equals 2 problem again. So the n equals 3 problem, its solution is really 2 applications of the n equals 2 problem plus 1 move of the big disk from its first home to its final home. So that's the way to think about the n equals 3 problem. It's really focusing on the n equals 2 problem twice and doing 1 move in between. Here's the challenge for you. Can you take that logic and solve the n equals 4 problem? Talk to your neighbor, talk to your teacher, use the Towers of Hanoi that's in front of you, and try your best at this using this recursive logic. And we're going to be back soon to talk about this.
Hi, I'm Dr. 4. Towers of Hanoi problem for n equals 4? No problem. I can do it and I don't even know that much math. What I do know how to do is delegate authority. Now, here's my n equals 4 problem for Towers of Hanoi. I'm going to solve it, even though I don't really know about how to do Towers of Hanoi problems. But my secret is that I know that to my right is Dr. 3. Dr. 3 is a whiz at solving the Towers of Hanoi n equals 3 problems. So what I'm going to do is I'm going to ask him to do most of the work for me. Now, I have my Towers of Hanoi problem. I'm going to pass it over to my right, and I have this note, and I'm going to give it with my Towers of Hanoi problem. What my note says is that I'm asking Dr. 3 to solve the n equals 3 problem and move the top 3 disks from the tower number 1 to the middle one, tower number 2. And then when he's done, to pass it back to me. All right, this is almost done. Now what I have to do is move the really large disk from this tower to tower number 3. And all I have left to do is to delegate authority one more time. So here's my second note, and I'm passing this problem along with the note back to Dr. 3. In this note, I'm asking him to move the 3 disks in the middle tower onto the tower number 3. And it's all done. And I didn't even have to do that much work. Ooh, Dr. 5. Please do the n equals 4 problem by placing the top 4 disks from tower number 1 to tower number 2 in the middle. What do I do now?
Welcome back, and thank you, Dr. Four. Dr. Four's real name is Anna Tatelman. She's a doctoral student in operations research here at MIT, and we thank her for her participation here today. Now, did you figure out what Dr. Four is to do with the note that she got from Dr. Five? Remember, Dr. Four can only knows how to do two things. She knows how to delegate authority down to Dr. Three, and she can move the largest disk in a pile of 4 from its original location to its final destination. So you probably figured out that with the note that she gets from Dr. Five, she should do the same thing. Delegate authority twice, and between delegating authority, and write notes at the same time, and between those two things, move disk number 4 from its original location to its final location. So if you did that, if you thought about that, that's absolutely correct. Now, when Anna, who is also Dr. Four, hands back the partially completed Towers of Hanoi to Dr. Five, did you figure out what else is going to happen? Yes. Dr. Five, who also only knows how to delegate authority down to Dr. Four, is going to send Anna back another note with another partially completed Towers of Hanoi and ask her to do the whole thing over again. She's got to write 2 more notes to Dr. Three, blah, 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 and that's the way the whole thing goes. So in general, you could be Dr. 17. Imagine a pile of 17 of these disks. And you could be Dr. 17 and say, no problem, I can work with that because all I know how to do is delegate authority. I'm going to write 2 notes. Each time I'm going to pass this to Dr. 16 here on my right, your left. And in between getting those things back, I'm going to do the largest disk, move it from its original location to its final destination. So no problem, Dr. 17, Dr. 42, or whatever. Still, the problem grows exponentially, and the amount of time it takes to solve this might grow very, very large, certainly larger than the amount of time you have in your classroom today. But I have a challenge now for you to show that you really understand how to delegate authority in this recursive way. If you can have 3 volunteers in your class, and they sit next to each other, and one will be Dr. 3, one will be Dr. 4, and one will be Dr. 5, and solve the n equals 5 disk Towers of Hanoi problem using the recursive logic we just had, where we're delegating authority on down the line, passing responsibility and notes back and forth. Do you think in your class now you can solve the n equals 5 problem? Now, n equals 5, 2 to the 5th, 32 minus 1 is 31. That's going to be a lot of moves. And I don't know how your class time is going today, so you may be a little bit stretched for time. So if you can't do the whole thing, start it. Be confident that you know how to solve it, and then you might abbreviate it if class time is short. Okay? So we need 3 volunteers, and maybe everyone in the class wants to do this and competitive, so you can have teams try to do this. Do this in your class, talk to your teacher, work with your neighbors, play Dr. 3, 4, or 5, and we'll see you soon. Welcome back, and congratulations, great teamwork. I know that the 3 of you playing Dr. 5, 4, and 3 did a wonderful job, and maybe there were multiple teams of 3 of you, each playing Drs. 5, 4, and 3. And what you did, the secret here is Dr. 5 and Dr. 4 continually reduced the problem to a problem previously solved. And Dr. 3 was the expert. He or she was the expert in solving the n equals 3 problem. So this method of reducing to a problem previously solved is called recursion. And we have a formal definition of recursion. Fasten your seatbelts. This is a little bit abstract, but we want to go and talk about it. So we want to define, recursion is a method of defining functions in which the function being defined is applied within its own definition. That is a mouthful. Let's say it again slowly, and then we'll give an example. Recursion is a method of defining functions in which the function being defined is applied within its own definition. Now you might say, what in the world does this mean? Well, let's take a simple function which you all know about, n factorial. N factorial is defined to be n factorial equals n times n minus 1 times n minus 2 times 3 times 2 times 1. You take the first n integers, you multiply them all together, and that gets n factorial. So a recursive definition of n factorial is that n factorial equals n times n minus 1 factorial. You see I have the function on both sides of the equation. Okay? Why do I do that? Well, I reduced following the calculation of n factorial to a problem previously solved, because I'm going to assume that I have calculated n minus 1 factorial over here. I just have to take that, multiply it by n, I get n factorial. So I could say n plus 1 factorial equals n plus 1 times n factorial, and continue on to larger values of n and calculate n factorial that way. So that's a simple example of recursion. Our solution to the Towers of Hanoi problem is a slightly more complicated example of recursion. Okay? And that's basically what we're doing today. Now, this is an optional stop point because you might be running out of time in your 50-minute or 60-minute class today, and that's okay. We have 3 more segments after this. If you have time today, or maybe some other day you want to go into the other 3 segments, which are a little bit more formal, a little bit more mathematical. And we look at the exponential growth thing and prove that, for example. Okay, but if this is a stop for some of you, I want to point to our website, which has additional resources. And you'll see a lot more information on the Towers of Hanoi there, including computer animation games that you can play. So if you don't have one of these to work with, a physical one, you can play it with animation games and color and these sorts of things. Play it as many times as you like and have a lot more fun, gain a lot of proficiency in solving Towers of Hanoi. Now, where is recursive thinking appearing in everyday life? Well, in American football, there's a football coach here actually in New England, near MIT here, who uses a fancy recursive method called dynamic programming. You can look it up on Google. Dynamic programming for figuring out what plays to call in a football game. We don't have time today to go into details, but there's a reference under additional resources which provides those details for you. Or a simpler example is a group of people who are exploring a cave. And they go into the cave, and there are a lot of juncture points where they have to make a decision as to what segment of the cave they go into as they're exploring. Suppose they explore for 4 hours, and they go through 12 different segments. Well, they have to figure out how to get out at the end. So they put trail markers at each of the juncture points showing, once you get back to that point, which cave segment you follow out to get out of the cave safely. So that's kind of recursive thinking. You know that you get to each juncture point, there'll be trail markers, and you have confidence that when you get to the end of that, there'll be another trail marker to show you where you go that way. So that's recursive thinking, exploring caves. So a challenge problem for you now in the class discussion is, in your class, can you find other examples of where recursive thinking might occur in your everyday life, or when you go out hiking or something, or playing sports? And for those of you who are leaving us today, thank you. We hope to see you again. And for those of you sticking with us, we'll see you soon in about 5 minutes. Welcome back. For those of you who are continuing with us today, I hope you had a nice discussion about recursion in real life. And now we're going to get a little bit more formal, if I can. Remember, we had the recursive equation for factorial. Let's get the analogous recursive equation for Towers of Hanoi. So, fasten your seatbelts, because we're a little bit formal here. So what is the solution to the Towers of Hanoi problem? First of all, the idea of a solution. Sometimes we think of a solution to an equation, it's a number. The solution to Towers of Hanoi is not a number, it's a set of moves. For the n equals 3 problem, it's a set of 7 moves. That's as efficient as we can be with n equals 3. N equals 4, it's 15 moves. Okay, so let us have some notation. Let us have some notation here. Let us have this notation, solution, SOL, parentheses, 4, 1, 3. You see it on your screen right now. Solution of 4, 1, 3. What does that mean? That means it's the optimal set of moves for an n equals 4 disk problem, where the disks originally are on tower 1, the leftmost tower, and have to be moved, following our 2 rules of movement, to tower 3, the rightmost tower. So that's the solution 4, 1, 3. And we can write a recursive equation, and we know what that equation is because we have seen how we can delegate authority on down the line. So here it is on your screen right now. So the solution for the 4 problem of moving from tower 1 to tower 3 is the solution for the 3 problem moving from 1 to tower 2. That's an intermediate move that clears the way to move the largest disk from its original location to its final location, the rightmost tower, tower 3. Okay, so that's the solution. That's called solution 1, 3, plus, again, the solution for a 3-disk problem moving from tower 2, the intermediate tower, over to tower 3. So when we say solution of 4, 1, 3, we're taking the 4 smallest disks and figuring out the optimal set of moves to move those from tower 1 to tower 3. There may be other larger disks under it. Maybe it's a 6-disk problem. We're just focusing on the smallest 4. Okay, so you see that equation on your screen. Now, what does plus mean in this case? So we're saying solution of 3, 1, 2 plus solution of 1, 1, 3 plus solution of 3, 2, 3. Well, the plus is not an additive sign like arithmetic. In set theory, it's the union of sets. So you see on your screen right now an image, for instance, for the solution of 3, 2, 1, we have 7 moves. And then for the 1-disk problem, we have 1 move. And then again, we have 7 moves. You sum those together, we have 7 items plus 1 plus 7. Add those together, we have 15. And we know that that is the optimal number of moves for the 4-disk problem. So that, in equation form, is the recursive equation for the Towers of Hanoi problem. Isn't that beautiful? Isn't that wonderful? So you could say it on words. So if you think you understand this, I have a challenge for you. The challenge is write the recursive equation for n equals 5. It shouldn't take too long. Write the recursive equation for n equals 5. Talk to your neighbor if you have a question or problem about it. And we'll see you again in a few minutes. Welcome back. Congratulations, because I know you did it for n equals 5. Wasn't too complicated. I'm convinced now you could do it for n equals 17 for any value of n. So that's great. Those of you who are interested in computer programming, using that recursive relationship, you can write a solution to the Towers of Hanoi problem with very few lines of code, and you just use recursion all the time. And you might even find on the web, and we have it on our additional resources, a video of a robot solving the Towers of Hanoi problem for a large number of disks. And I'll bet that robot was programmed with the recursive relationship that you now know. So congratulations. We have something left over that we never proved. We speculated that the size of the problem grows exponentially. Basically, for every new disk that we add, we double the number of moves we have to make to solve the Tower of Hanoi problem. But we never proved it. So let's do that, because it's going to be easy. There's an equation involved. Let's have an operator called count, C-O-U-N-T, count, and we'll put count here and solution here. So count of solution of 3, 1, 3 would be the count of the number of moves we have to make to solve an n equals 3 disk problem. We know that's 7. We know that's 7 for 3 disks. So we have the count operator over the solution, and all we're doing is counting up the number of moves to do that particular solution. So we can take the recursive equation that we had last time and put a count in front of each of the 3 terms on this side and in front of this term on this side. Okay? So we then get, and you see it on your screen right now, the following equation that says count for the n equals 4 problem, moving all 4 disks from tower 1 to tower 3, equals the sum of 3 other counts. The first one moving 3 disks from Tower 1 to Tower 2, then moving the largest disk from Tower 1 to Tower 3, and then moving the 3 disks that are parked temporarily on Tower 2 over to Tower 3. 7 plus 1 plus 7 is 15, 2 to the 4th minus 1. So that's what we have for the count for 4, for n equals 4 disks. Suppose we hypothesize that the count for an arbitrary n number of disks is 2 to the n minus 1. 2 to the n minus 1. So if it were, let's say, n equals 5, 2, 4, 8, 16, 32, subtract 1, that would be 31 moves, okay? Suppose we hypothesize that the count for the n disk problem is 2 to the n minus 1. Then if we plug back in for the count for an n plus 1 problem, we see, and you see the equation on your screen right now, and we work out the 3 terms on the right-hand side, which assumes that the count for the n disk problem is 2 to the n minus 1, we see that, aha, then the count for the n plus 1 problem is 2 to the n plus 1 minus 1. That's recursion. That's iteration. If we know it's true for a small value of n, we know it's true for the next larger value of n, and then it's true for the next larger value of n, and so on and so on and so on. Ladies and gentlemen, we have proved exponential growth. This kind of proof is called proof by induction. You may or may not have seen this before. Proof by induction deserves its own Blossoms module. We don't have time today to do that, but I thought this is a nice way to show that the exponential hypothesis that we had way back, I think in segment number 2, is in fact true, and we proved it. So congratulations to you. Now, that was a little bit of, you can unfasten your seatbelts now because I have a fun challenge for you. There is a myth, there is a legend, that in South Asia somewhere, there exists some monks in a monastery, or priests. And they have a very large, much larger than this, a very large Towers of Hanoi problem. How large is it? 64 disks. And they're very efficient. These monks really are very efficient. They know how to make every move optimally, so they never make a mistake in terms of the moves. And they work 24/7 on this. And they move 1 disk every second. 1 disk every second. Every second of a minute. Every minute of an hour. Every hour of a day. Every day of the week. Okay? As long as it takes. So here's your challenge. How long will it take these monks to solve the n equals 64 problem? Will it be 1 day? I want you to vote and share it with your teacher. 1 week, 1 month, 1 year, 10 years, 100 years, or longer. Vote first. Let your teacher put that up on the blackboard about your votes, and then do the calculation. See if you can estimate how long it would take these monks to solve the n equals 64 problem doing 1 disk move per second. This should be fun. See you soon in a few minutes. Welcome back. We're at our concluding segment for this Blossoms module on Towers of Hanoi. And I'm sure you had an interesting and fascinating discussion about the mystery of the monks with the 64 disks in their Towers of Hanoi. On your screen right now, you see the number of seconds it would take for those monks to solve this Tower of Hanoi problem, assuming they make 1 move per second, and they're very efficient, they never make an error. Okay, now, you probably didn't get to that exact number because that takes a lot of calculation to do, but maybe you approximated it in certain ways. But if you translate that into years, and to do that, you have to figure out how many seconds there are in a year, and I know you know how to do this. 585 billion years. Do you know the planet Earth is only 4.567 billion years old? I bet you know that because we have a Blossoms module on geologic time, and it talks about that. Okay, so those monks are going to be working for a long time, and obviously that's an intractable problem when n equals 64 because of the exponential growth. It just shows you the power of exponential growth. Okay, there's one last thing we should discuss, And that is, suppose you yourself have to solve a Towers of Hanoi problem for, let's say, n equals 6, n equals 7, and you don't have Dr. 4, Dr. 3, Dr. 2, all these doctors next to you to do it. You have to pretend to be the doctors yourself, thinking this recursive way that we've framed and formulated and solved the problem. So we're not going to create a recipe for you, because if it's a recipe that you memorize, then you're going to forget the beauty of recursion. You have to pretend to be Dr. 3 and Dr. 5 and Dr. 7. You have to pretend to be those doctors when you're doing this. But here's one of the key hints. What do you do on the first move? Where do you take the smallest guy, the smallest disk, and where do you put it? So let's go and look again at the n equals 3 problem. Okay, here's the n equals 1 problem. This is simple. We just take it from Tower 1 to Tower 3, and we're done. Okay? Now, if we have the n equals 2 problem, an even number of disks, our first move is to Tower 2, then to Tower 3, and then to Tower 3 again, and we're done. Okay? So, suppose we have 3. Suppose we have 3. So our first move is to Tower 3, then to Tower 2, then to Tower 2, and like this, and we're done. Our first move is to Tower 2 if the number of disks is even, and our first move is to Tower 3 if the number of disks is odd. So that's a hint on how to get started. But we're not going to have a recipe for the whole thing. I want you to convince yourself that that's correct. And then you can think about, over time, over the next day or week, how you might do this for, let's say, an 8-disk problem if you're doing this yourself, thinking recursively. So you can work out the details. I know you'll have fun doing it. You can do it with your friends. So thanks for your attention. We've had an interesting ride. A couple of times you fastened your seatbelts, and you survived that, which is good. And going forward, may all of your complex problems be reduced to a sequence of previously solved ones. See you soon. Hi, I'm Dick Larson. I'm, I guess, the architect of this Blossom's module on Towers of Hanoi, and this is a video teacher's guide. So if you're joining us here for the first time, welcome. If you've looked at the module first, welcome here too. Basically what we have here is a highly interactive, problem-based experience for your students and yourself to learn about recursive thinking. And this develops a critical thinking skills in them to look at a problem which is kind of complex, but we can make simpler by redefining it in terms of a sequence of simpler, previously solved problems. We've designed it with no formal prerequisites at hand. It should be accessible to any high school math class which is college-bound. Now, you might say, well, don't they have to know anything? It would be nice if they have experienced set theory, but it's not mandatory. It'd be nice if they have experienced exponential growth, but that's not mandatory either. Okay? And even the beginning parts of the module could be accessible, I think, to middle school students as well, not the end parts. So the end parts where we have mathematical proofs of recursion and exponential growth, probably those are at the junior or senior level for college-bound math classes. Now, it's important that every student have a Towers of Hanoi in front of them. And I doubt whether it's going to be as fancy as the ones we used here in this module. But even if they just have a stack of 5 coins, each with a different radius, with the smallest one on top and the biggest one on the bottom in ascending order, or it could be metal or rubber washers they get from a local hardware store, they could assemble their own Towers of Hanoi, put it on a piece of paper, and put 3 dots on the piece of paper as to where Tower 1, 2, and 3 would go. They can do it that way. But it's important that in your class you have at least one physical Tower of Hanoi, so that the students, when they play Doctors 3, 4, and 5, can pass it back and forth to each other. So your class hopefully will have at least one. And as you've seen, and they show it on the screen right now, it's me making my own Towers of Hanoi for less than $2 from the local hardware store. I did this last weekend at my home. Okay, that's the background. Now let's go to some advice for you for each of the breaks. First, for activity 1. This is basically just so the students can get some familiarity with the problem. They work with the problem, get comfortable, they know our two rules, and they try to solve the n equals 3 problem in a minimal number of moves. A few will get it. I would say most will not, but that's okay. And it's just to get them familiarizing with the general problem, and that's the focus, and you can help them with that focus in activity 1. Okay, for activity 2, it's pretty simple. We see that for n equals 1, there's 1 move. For n equals 2, there's 3 moves. For n equals 3, the best we can do, it seems, is 7 moves. So it's to get the students to think, how fast is this growing? Well, it's almost growing as 2 to the power n. And so you as the teacher can guide them. In fact, you might want to, once they get the hint, you get some hints, you might actually even show in the blackboard 2 to the power n for n up to 7 or 8 or something like this. And then they'll see that, gee, it looks like this grows as 2 to the power n with a little bit of a tweak, and the tweak is -1. And we don't prove it, but it gets them into the problem. It gets them into the problem so that they understand that the problem grows, basically almost doubles each time you add a disk. Activity 3 continues a discussion of exponential growth. And in that segment, I discuss the exponential growth and say, it looks like that's our hypothesis. Let's hold on proving that till later. And that's okay, because we're getting some intuition now and some knowledge of the problem. And then basically, we ask them to think about patterns. So if they mark down each of the 7 moves they make in solving the n equals 3 problem, they'll see things like certain patterns, like the smallest one has moved every other move. The biggest one has moved just once from its initial location to its final destination. And the middle one is moved twice. And so for them to think of those patterns and, gee, from those patterns, is there anything we can do to extend this more generally? I don't expect them to come up with a recursion idea. They'd be very, very, very bright if they did this. But at least they can start to see that there are some patterns here, and that's the objective of this break. In activity 4, we have basically shown for n equals 3 that we really just solved the n equals 2 problem twice, and in between each of those solutions, we moved the biggest of the 3 disks from tower 1 to tower 3. So basically solving for n equals 3 just involved solving n equals 2 twice and plus making 1 move. So we want them to think about how they might apply that to n equals 4. You can help them and guide them. Some of them will figure this out. Some of them will not. We want them to talk with their neighbors, figure out strategies. And again, you can see this is experiential learning, problem-based learning. As they delve more deeply into it, they get more involved, they get more intuition, and they get more understanding of the problem. Now to activity 5. This is after our guest appearance by Dr. Four, otherwise known as Anna Tatelman. And this is the segment that probably is going to require your most detailed attentiveness, because Dr. Four just asked a question to the audience, to your students. What do? I just got this note from Dr. Five. And so you have to encourage the students about how to think about this, and you encourage them to say, well, Dr. Four only knows how to delegate authority. So you might show the note again to them, the note that she got from Dr. Five. And basically, Dr. Five is asking Dr. Four to assemble the top 4 of the 5 disks onto tower number 2. So Dr. Four only knows how to do one thing, and that's delegate authority. So she has to write a note to Dr. 3 to say, initially, to take the top 3 of the 5 disks and move them from tower 1 to tower 3. Okay, she puts that note through along with the Towers of Hanoi, and back it comes, and those 3 are assembled onto tower 3. And then Dr. Four knows how to move the largest remaining disk on tower 1, which is the next to the largest disk. She moves that onto tower 2, and then she has to write another note that says, reassemble the 3 disks that are on tower 3 and put them back onto tower 2. She writes that note, hands it to Dr. 3, and out it comes. So basically, it sounds a little bit complicated, but it really is not, because all Dr. Four is doing is delegating authority twice and moving the one larger disk once. That's all she knows how to do. Once she gets that second thing back from Dr. 3, she smiles and hands the partially completed Towers of Hanoi back to Dr. 5. And then you might say, well, what's going to happen next? Well, what's going to happen next is there's going to be another note, and the thing is going to come back again and say reassemble some things on the other tower. Okay? And so you might talk about that. And then once the students understand this whole process, they'll understand the entire recursion. This is probably the most complex of the breaks and will require your diligent attentiveness to these issues. The rest of the activities are a lot simpler. Okay? So basically for activity 6, you ask for 3 student volunteers. And if there's lots of excitement in the class, maybe you'll get 9 student volunteers, in which case you create 3 teams, teams 1, 2, and 3, or A, B, and C, whatever. And in each of the teams, there's a Dr. 3, Dr. 4, Dr. 5. And you start off the whole process with Dr. 5, and she or he delegates authority down to 4. 4 delegates authority down to 3. And 3, we assume, knows how to solve an n equals 3 problem efficiently in 7 moves. So there's no need for a Dr. 2 or not Dr. 1. If the students don't like that, you can put in a Dr. 2 and move on down the line. That's okay. But basically then, the idea is to see if these 3 students, following our recursive ideas, can solve the n equals 5 problem. Depends on how you're doing in your class with regard to timing. They may not be able to have time to do all 31 moves. Maybe they just do the first 10 or 11 or 12 moves to show that they know what's going on. And that would be fine. And that's the end of that segment, that break. Activity 7 is we formally introduce what recursion is. So we give the formal definition. It's a mouthful. I repeat it once or twice. And then we give an example of n factorial. And I challenge the class, and you might want to ask them about it. I say, well, if you could take 10 of you in the class to do factorial, 10 factorial recursively, how would you do it? You might even want them to do it during this break. They line up, and each one will take the number given to them by the adjacent one next to them and multiply it by their standing in the line. So for instance, if I'm number 7 in the line, I'm going to take whatever number is given to me by number 6, multiply it by 7, and pass it on to the person to my left who's position number 8. And that's the way the students recursively, with 10 students participating, can create and calculate 10 factorial. If they could do this in this break, they would really demonstrate they understand experiential recursive thinking. At the end of this break, you may decide that this is the conclusion for the first class, because probably by the time you get to this point in your class, a 50 or 60-minute class might be over. And the final 3 segments are also mathematically more involved. So I would suggest that in the first class, you stop here, unless you have a 90-minute or 120-minute class and you want to go through the whole thing. And so you might want to visit the next 3 segments tomorrow or next week or some later time. In activity 8, the break should be really short because we showed and argued the validity of the recursive relationship for the solution to the Towers of Hanoi for the n equals 4 problem. And we just asked the students to write down themselves the solution to the n equals 5 problem. And it's basically the same equation, but you replace the 4 with a 5, and you make equivalent changes on the right-hand side of the equation. And if they know what they're doing, they'll be able to do this definitely within a minute or so. You might get some questions from them, be able to answer them, and we come back from that break. Activity 9 involves 2 things. It's perhaps their first exposure to proof by induction, where we actually prove the exponential growth in the number of moves they have to make as this problem increases in size. And so it's a good exercise for them to understand the power of exponential growth. And so that's one aspect of what's going on here. Whether or not they've seen proof by induction before, it's okay, because we try to do it in a gentle way where we don't invoke a lot of theory and formulations. And after that, they get this fun problem with the 64 discs with these monks or priests in a monastery. And I don't expect them to come out with that exact number, 2 to the 64 minus 1 that we showed on the screen. But here's a hint. 2 to the 10th is 1024. So you could tell the students, they can approximate this. We want to get an order of magnitude. So how about approximating 2 to the 10th as 1,000? So instead of 1,024, the exact 1,000. And then you can approximate 2 to the 64 as 1,000 times 1,000 several times, and then 2 to the 4th at the end. And you get an answer that's very, very close to the exact one by approximating. And the key is for them to see it's hundreds of billions of years, which hopefully should be a big surprise for them. Okay, the number of segments is 10. So at the end of segment 10, there's no formal activity that we talk about. But hopefully, if we're successful at that time, the students will be abuzz with excitement. They will have learned how to approach the Towers of Hanoi problem in a recursive way, hoping that they can solve it in various recursive approaches that we've talked about. They will have seen the power of exponential growth. They will have seen proof by induction for the first time. They will have seen applications of recursion in everyday life and other mathematical situations like n factorial. Maybe they've done this experientially in their class. So if you have any time left by that time of day, it would be great to guide the students in a discussion about what they think went right, what they think went wrong. Are they still confused about a few things? And how they see that recursion could occur in their own lives. So we hope you've enjoyed this. Thank you for selecting this segment and for this Blossoms module. And if you have any questions or issues, please feel free to email me, rclarson, Larson, at mit.edu. I hope to hear from you and have fun with this module. Thank you. We cannot move 2 at a time. We can only move 1 at a time, okay? Second rule is that anytime we have a pile of disks, we must have them in ascending order, with the smallest one on top, the biggest one on the bottom. So this is not allowed, okay? But this is allowed. So those are the 2 rules we have to obey. And let's see how we're going to do this. Let's go over to the small one. Here we are with the small one, and we have a lot of disks. So let's not start with the largest problem. Let's start with the smallest problem. If we had to move this pile of disks, 1 disk, from Tower 1 to Tower 3, all I do is pick it up and put it over there. It took 1 move to do that. So that was easy, okay? Let's try it with 2 disks. Here we have 2 disks. How do I move this pile of 2 disks from Tower 1 to Tower 3? That's easy. I put this smaller one in a parking space, Tower 2. I put the larger one in its final destination. And then I take the smaller one off the parking space, put it over here, and solve it. That solves for the n equals 2 problem. So now I have a challenge for you. We have solved the n, and I put it there. And I take the medium one, I park it over there. And I have to move the smallest one again. That's the only move I have. I put it over there. I'm not making much progress here. I'm not making much progress here. If I put that over there and this over there, this doesn't seem to be working. And look, what I've done is I've made the pile on the intermediate tower. Now, did I tell you when I first learned of this problem, the Towers of Hanoi, several months ago, it actually took me several hours to figure out the solution and then the beauty of the recursion that we're about to talk about. So let's go back here and see if we can do a better job at this. So I take the smallest one and park it over there on 3. I take the medium one and park it on 2. And then I take the smallest one and put it on top of medium. And then I move just once the largest one from 1 to 3, its final destination. I take the smallest one, put it over there as a parking space. like this, and like this. And lo and behold, I've done it, and it took me 7 moves. The first time I did it, it might have taken me 11 or equals 1 and n equals 2 problem. Let's go to n equals 3. So in the tower in front of you, whether it's coins or washers or homemade tower, put 3 discs on tower 1, obey the rules, move them over to tower 3, discuss the strategy with your neighbors, okay, and record the number of moves it takes you to solve the problem. Okay, so solve the tower, the n equals 3 problem with the Towers of Hanoi, and do this in your class for 3 or 4 or 5 minutes, and we'll see you soon. Welcome back. Were you successful? Were you able to solve the n equals 3 disk problem? And did you talk to your neighbor? And did you keep count of the number of moves it took you to solve n equals 3? Well, and let's remember what the rules are. The rules are you can only move 1 disk at a time, and any pile of disks on tower 1, 2, or 3 must be in ascending order with the smallest one on top and the biggest one on the bottom. So I hope you remembered to obey those rules when you worked with your neighbor and yourself and you solved the n equals 3 problem. Now let me try to do it over here. So suppose I take the smallest one, investment. It could be coins, 4 or 5 coins on top of each other, small ones and big ones. Or you could even make a Tower of Hanoi like this at home. And this about 3 days ago, I made this Towers of Hanoi in my home in Lexington, Massachusetts. And you might see a photograph or 2 of the production process, what's going on here. And basically, these discs in the towers are nothing more than washers that I got from a local hardware store. They just cost pennies a piece. And the wooden dowels here that I cut here cost less than $1. And this was a piece of wood that was left over. So you can make your own Towers of Hanoi like this if you want. Okay, so what is the problem? What are we trying to solve today? Well, let's look at this. What we're trying to do is move a set of disks like this. We're going to call each of these things a disk. Some have a smaller radius and some have a larger radius. Our chore is to move this pile of disks from here. We'll call this Tower 1. The medium one we'll call Tower 2. And this one on your far right we'll call Tower 3. We want to move these disks over to Tower 3. But we have 2 rules. We have 2 rules we must obey. Hi, my name is Dick Larson. I'm a faculty member at MIT, Massachusetts Institute of Technology in Cambridge, Massachusetts. Welcome. Today we have a very interesting problem for you. It's called Towers of Hanoi. It's a famous problem that has applications in computer science, in mathematics, and as we will see, in everyday life. Now, this is not a new problem. Towers of Hanoi was proposed in 1883 by Edward Lucas. You'll see on the table in front of me here, I have 3 physical representations of the Towers of Hanoi, what I call big, medium, and little. And we're going to talk about the rules of this game and what we're trying to do. And each of you should have a Towers of Hanoi in front of you. Now, these 3 were made professionally, and they cost some money, not too much, but some money to purchase. But you can make a Towers of Hanoi with just a minimal